Thank you for the introduction and also thank you for the invitation. It's my pleasure to be speaking in Sogang University about the fortuity program. So this fortuity program is also known, referred to as the black hole cohomology problem, but it has become, as you will see, it has become a little bit more general than the black hole cohomology problem, so we needed a better name for that. You might have heard something about the fortuity program because recently many Koreans are working on it. And whether you have or have not, I hope this will be a good opportunity for all of you to get to know what is going on in this program. So what is the fortuity program? Click here, maybe. Yes. Then, so what is the fortuity program? It is a series of work by many people, including myself, with a shared goal of understanding quantum microstage of supersymmetric black holes by identifying, counting, and writing down the quantum microstage. Well, that have been one of the biggest goals of the entire community for like decades. And what is so special and new about this program? What makes it a step forward, what makes this fortuity program special is this new scheme for classifying supersymmetric stage or operators in finite n-gauge theories into two categories. The first category is called the monotone stage or operators. They represent gravitons in holographic theories, and they carry some properties such as being light, scarce, ordered, or systematic. As the name suggests, it is less interesting objects. The real interesting guys are the second category, the fortuitous stage or operators. They are heavy, abundant, disordered, and chaotic, but most importantly, they represent black holes in holographic theories.
I think I can understand that. What do you mean by scarce here?
Scarce means in holographic context, it doesn't account for the black hole entropy. There's not enough number of monotone operators to account for the black hole entropy. And in holographic theories, the typical microstate will turn out to be fortuitous.
So you're saying, for example, some fixed charge, the number of monotone states are not that large compared
in fixed charge if you choose large enough charge.
Large enough.
That will be a little bit more clear as I introduce further. I hope. And if it doesn't, please ask.
Can I ask a question?
Sure.
Actually, this was a question that I have been asking when I met a person who is working on the fortuity program. So you're assuming a finite n.
Yes.
And suppose we have a stereotypical ID5 to 5 geometry. And finite n means the gravitational constant is large.
Yes, exactly.
And can we define graviton?
I think that will all be a little bit more clear in the next slide. It seems like this fortuity program has been introduced to all of you by many Koreans, so everyone knows it very well. But let me introduce it. So I will start by introducing the history of this program, because as a way to motivate this program, because the history will make it quite obvious that we really have to classify the operators in this way. In particular, the history will make it clear that we really have to consider the effect of finiteness of n. And thinking carefully about the effect of finiteness of n, it will naturally lead us to classify the operators into these two categories. And then I will introduce some progress that has been made in this program over the last few years. Much of the progress has been made in the benchmark theory, which is the n equal 4 Yang-Mills with finite SUN unitary gauge group. But also many progress has been made in other theories, other holographic theories such as ABJM theory, but also curiously non-holographic theories without black holes. Each theory teaches us different lessons, but I will focus on one of them to talk a little bit about the quantum correction to the supercharged and the quantum correction to the fortuitous operators. And then I will discuss a little bit about what this fortuity program really tells us about the black hole themselves. In particular, I will discuss how the fortuity incarnates in hairy ADS black holes. And then I will conclude with some open questions. So let's get started with the history. Something we've known for many decades is that black holes have entropy. And that means, according to Boltzmann, there should be as many quantum microstates of the black hole. Counting this microstate has been a very successful theme in string theory, as we all know. And shortly after this milestone, the stage was set up for ADS black holes. So there are ADS black holes, and dual to them, there should be as many quantum microstates in the dual CFT. The correct and very powerful tool for these quantum operators is the 1/16 BPS index. It can be understood as some kind of a partition function that counts the number of bosons minus the number of fermions in each given microcanonical charge sector defined by a fixed charge J. I'm going to use this single charge J for simplicity as the overall amount of the charges that an operator carries. But of course, the index can be further refined. For example, in n equal 4 Mills, there are 2 angular momenta and there are 3 R charges. And you can introduce fugacities for 4 out of 5 charges to refine the index and write it as a function of 4 variables. This index is supposed to count exactly what we are looking for: the gauge invariant BPS operators in the dual CFT. In this case, n equal 4 Mills on R4. By BPS operators, I mean the operators that are annihilated by supercharged Q and its conjugate Q dagger. But by Hooch theorem, an operator annihilated by both Q and Q dagger is in one-to-one correspondence with the cohomology classes of the supercharged Q. So for this reason, I will often abuse the terminology to not distinguish between cohomology and the operators. But to be precise, a cohomology refers to a set of operators, or any one of those set of operators that are cohomologous to the actual BPS operator. So these gentlemen, they developed and computed this 1/16 BPS index for large N. They used matrix model technique to evaluate this index at large N, because that was kind of the hot method at the moment due to this famous work just 2 years before. They computed the index. And disappointingly, this index did not fulfill the black hole-like growth, the black hole entropy. But instead, this answer matched precisely the ADS 5 times S5 supergraviton spectrum. They also wrote down the BPS operators that are supposed to be counted by this large N answer. That was this single trace symmetrized scalar operators. They're superconformal descendants in the commuting subalgebra with the supercharge. And from these single trace operators, we can form a complete Fock space with multi-trace operators from these. That constitutes the supergraviton spectrum in ADS 5 times S5.
Just a quick question. Could be a basic question. When you say it matches the supergraviton spectra, so now the index is computed in canonical ensemble as a function of tau, but not sure. So when you say it matches the spectrum, what was the actual match? Like you changed the ensemble, so you got the index, like as a function of charge, you got the index, and then in the dual gravity side. So how the index is compared with the supergravity?
That is a little bit subtle question. So there are 2 points of view that you can take on the index. You can view it as a microcanonical thing or a canonical ensemble, meaning that if you put some definite value of t here and sum over all the series expansion, that will give you some number. That's the canonical view, but you can also consider the individual coefficient in the series expansion like this. So what these people did is the canonical point of view.
And then in the gravity side, you compute something that matches the data function as a function of tau.
That's a very good point, because they didn't write in this form, but this is a new modern microcanonical rewriting of their answer, but it's basically the same answer. But yes.
In any case, they derive the same thing from both sides and match, even though they did not write that in terms of eta function.
Yes. So computing in the matrix model technique, it's written as it's written in some form, and that could be matched with the ADS 5x5 supergraviton spectrum, which is actually a little bit different from this. I wrote it like this to write it in a simple way, but yes, maybe this could have been mistaken in that sense. But anyways, the bottom line is that for infinite n, for strictly large n, the index was computed by these people in 2005 already. Also, the entire set of BPS gauge invariant BPS operators that are being counted by the index were written down. The only problem is that the black hole was missing. It's all gravitons. So where are the black holes? I think this connects to the question that you asked earlier. In gravity theory, black holes with certain charge, infinite J, the charge of the black holes, including its energy, is supposed to scale in g-Newton. And that translates to 1/n² by holography. So that means if you want to consider a CFT operator that is dual to a black hole with certain gravitational charge J, the capital J, then you have to consider infinite lowercase j, which is the CFT charge. You have to consider operator with a CFT charge that goes to infinity as n² to make the gravitational charge finite. Turning the logic, if you want to write an operator, a black hole-like operator with finite amount of ink or finite amount of time, that means finite j, finite lowercase j, you really need the finite n. So this history is motivating us to investigate what finiteness of n has to offer. So as we have seen, there are complete set of graviton operators, these single trace operators. And now let's see what finiteness of n does to these graviton operators. Between finite-sized, say n by n matrices, if you have more than n such matrices, the multi-trace structure built out of these matrices are no longer independent, but there are mathematical identities known as trace relations. What these relations does to these graviton operators is obvious. Now there are relations between these multi-graviton operators, reducing the number of such independent graviton operators. But this is not what we wanted. We wanted more operators. It turns out that this finiteness of n has more intricate second effect on the spectrum of BPS operators. It can actually produce a new class of BPS operators. That can happen when a supercharged Q acting on an operator O is itself a trace relation. That means it will vanish only for certain small n where the trace relation holds.
Sorry, so one question. So according to your statement in the last slide, in the last line, then I'm just looking at this. So if you increase n, capital N, but scale have like J also, the CFT charge also scales like n².
Yes.
Then in principle, you can think about the dual black hole.
Yes.
So you might be able to think about the number of CFT states dual to such black holes. So that means this finite n effect, is it actually finite J over n effect? Or because if n over J is finite,
Yes.
you can think about black hole.
If n over J is finite, but you want to take
N to infinity.
large n,
Yeah.
you will need infinite amount of ink or
Yeah.
time. Yeah.
What I mean is just in principle, like counting BPS operation might not be easy, but what I'm saying is when n goes to infinite, but charges are also going to infinite. So you have to look at very like the coefficient of this expansion in the infinite order, at some infinite order. But in principle, you can see this kind of effect still there.
Yes.
Like
Yes.
yeah.
Yes. Even if you take n equal to infinity, then you will need a lot of time and ink to write down the operator. But then there are so many matrices here,
Right.
and there will still be trace relations between them.
see.
So that's one scaling argument. But the point of view that we are taking is that we want to write down the operator.
Yeah.
We need a definite form of the operator. That means we have to limit the number of matrices that appear. Then we have to consider finite n.
So you mean that when we have an infinite n, then the dual operator or state for a black hole can be infinitely long and complicated, right?
Yes, exactly.
But how about like finite n such as n equal 1 or 2? Then black hole may be simplified. How about gravitons?
Gravitons all look like this. And using these operators, you can form any, from simple to heavy operators using this.
They represent gravitons when we have an infinite n, but do they represent graviton if we have finite n?
So that's where your previous question comes in. So when n is finite, what does graviton mean? I mean, the duality between the CFT and the supergravity works when n is large, right? So when n is becoming finite, we are in some way working on the extrapolation of the gravity theory into quantum regime. So something you would call quantum gravity. And maybe it is not a well-defined notion to talk about gravitons in such a quantum gravity theory. What's the extrapolation of the supergravity? But the sense is that in large n, there are graviton operators, and these are the answers that was counted by Kinney and Maldacena in 2005. These are gravitons for large n. And as you take n to finite, there will be relations between these operators, but there are certain still, these represent certain operators. And let's take that as an extrapolation of gravitons into quantum gravity.
If we think in the way of like cyber-Wilson theory, so suppose we have two polar monopole, and in such theories, since we have a gauge theory, we have like electrons, which is a perturbative excitation of Yang-Mills theory, but we also have magnetic monopole. Yeah, but that is non-perturbative. But if we have imposed the electromagnetic duality, then electric field, which is analogous to the graviton, becomes non-perturbative in the duality transformation. And the magnetic monopole, which was non-perturbative, becomes perturbative in the duality transformation. And it looks like that. Like, in the large n limit, the black holes are...
I don't understand. So your question was like finite and graviton interpretation, right? Is it valid?
So my question is, can we introduce some concept of interpolation or something like that in this situation?
So the magnetic monopoles and non-perturbative phenomena are indeed very, I guess, to say the least, hard to understand. And probably what I said about this extrapolating the notion of gravitons probably doesn't apply to the non-perturbative objects. So yes, that is a good question. And so that is one point where this distinction between gravitons and black holes that I'm calling, this classification of gravitons versus non-gravitons or black holes, are they really equivalent to the monotons and protons that I will soon introduce? That's a not waterproof part of this fertility program. So that's one interpretation issue that is worth thinking about in this program. Thank you for the good question, and please feel free to ask more questions. So anyways, in this way, the trace relations, despite being relations, can produce rather than reduce the new class of BPS operators. And it is by this mechanism that the BPS operators could account for the black hole entropy that these graviton operators alone could not. So these two effects are clearly visible in a concrete finite and index computations. So in this picture, the red lines, actually the red dots, represent the coefficient, microcanonical coefficient of the infinite n index that Kinney, Maldacena, Minwala, Raju in 2005 computed. And then the other dots are the same index for n equal to 2, 3, and 4. You can see that for small j, small charge j in small order, because of this first finite n effect, the number of operators are reduced compared to the infinite n. But soon enough, the second effect kicks in, and the number of operators actually increases for finite n. And this is enough to account for the black hole like growth as you take finite but large n.
Is it the number of operators which correspond to black holes?
Well, this is an index, so that means it just doesn't distinguish between any gravitons or black holes. It doesn't have any interpretation like that. It's just the total number of any operators with certain microcanonical charge.
Horizontal axis is J or?
Yeah, this is equivalent to J. So it's the overall. It is written N in this paper, but it's equivalent to the overall charge J. And now this second finite n effect that defines new class of BPS operators can be formalized into more general theories. So consider suppose you have a series of theories that are labeled by n, such as gauge theories, and you can define a definite form of operator throughout these theories for all n. Now, if you consider this definite operator for all n, it can be classified as a monoton if it is BPS for all n. On the other hand, it will be fortuitous if this operator is BPS only for certain small n, which means that it has become BPS thanks to this second finite n effect. In holographic theories, these monoton versus fortuitous operators, I can classify these as gravitons and black holes. It's not a waterproof argument, but according to the argument that I gave for this motivating example, that applies to any ordinary holographic theories. Because if you have an operator, and if you have an operator, it's not a black hole if it's still in the BPS spectrum as you take large n, which means you're turning off G Newton. If you turn off the G Newton, but it's still in the spectrum, it's not a black hole. These monoton operators have a property of being systematic. You can systematically generate in this way all the graviton operators and count them modulo these trace relations. But the fortuitous operators are more erratic in nature. They happen by a lucky chance, which is the dictionary definition for the English word fortuitous. So this is the end of the foundational part, and I will proceed to introduce the progress that has been made in this fortuity program. So I will first introduce the progress in N=4 theory with unitary gauge group, and then I will turn to other theories. Before I introduce the actual results, let me bring up 3 points to have in mind when looking at the actual results. The first point is that I'll be restricting to the so-called BMN subsector. It means that I will restrict to operators that are written with these certain kind of fields, the scalars, chiral linii, and gauge field, but written without gaugini or derivatives. This truncation is consistent or closed according to the supercharge only at the classical or tree level of the supercharge. And by this, I am assuming that we'll be working in the weakly coupled regime of the Yang-Mills theory, where we can consider just the first order of G Yang-Mills. The reason for making this kind of truncation is obvious. We simplify the problem by only considering a subset of all the operators. But importantly, this consistent truncation, this BMN subsector, contains the black hole. So it is an ideal balance point where you simplify the problem a lot, but still keep its essence. The second point is about the two-step procedure of counting and then constructing the operators. It is relatively easy to count the operators because we can use the index. We can compute the full index of the theory within the BMN sector, and then we can also compute the index only over the monoton, the graviton operators, because as I told you, they are systematically generated we can systematically compute the index over monotone operators. Then this difference, the fortuitous index or the non-graviton index, will tell you about the quantum numbers and degeneracies of the fortuitous operators. With that information, it is not only easier to explicitly construct the fortuitous operators, but that will also hint you towards the organization of the fortuitous operators related to the next point. So we'll be writing a lot of fortuitous operators, but they are not all random and unrelated. There will be certain core fortuitous operators, and there will be fortuitous operators that follow from the core operators in some way, in some sense. There are three senses in which the non-core fortuitous operators can follow from the core. One, the superconformal descendants. If you have a primary operator, each superconformal descendant will be automatically fortuitous new BPS operator. Two, graviton dressing. Some operators will turn out to be a simple product between a smaller core operator times a simple graviton operator. And that we interpret as a graviton dressing a core black hole. Then there will be a more mysterious class of operators that we call brane dressing, brane or dual giant graviton dressing, that I will introduce in the next slide, in 2 slides.
It's a very basic question. So when you want to compute this fortuitous index, you said from the original superconformal index, you subtract the graviton.
Yes.
So the original superconformal index is probably the Kinigan plus Kinigan.
Yes, what you compute using the matrix integral.
Yeah, and the graviton index is basically formulated in the same way, but in the plasticities expansion, you only keep track of graviton, or
It is not really. So to talk about the methodology to compute the graviton index, it's really a counting. You construct all the graviton operators that look like that.
it's not from matrix model.
It's not.
Wow,
You construct all the graviton operators, will find the trace relations between them, and just count the remaining independent numbers of them. It is not easy, but it is easier than writing the fortuitous operators.
Okay, some question. So when you mention the graviton dressing, is graviton massless here?
Yes, gravitons are massless. It's
And
gravitons.
however, there can be some momenta, right?
Yes, they carry charges and momentum. Yes.
So as a result, without dressing the object and with dressed object, the total energy or total mass would be different in general, depending on the graviton momenta.
Yes, yes. So in operator language, if you multiply a core black hole operator with a graviton operator, the total amount of charges, R charges and angular momenta, will simply add up. And for the gravity interpretation, we interpret as the charges being simply the sum of over two parts of the systems, assuming weak interaction between them.
So graviton carries all the charges of the angular momenta and the R charges?
In general, in gravity picture, it's the black hole that carries most of the charges, and graviton will be a simple small perturbation of that. But in operator picture, it can be not so hierarchical. So in operator language, there will be a core part and a graviton part, and simply the charges and angular momenta of the two parts will simply add up. And it's not necessarily that one is larger than the other.
Okay, thank you.
You have mentioned that if we have a fortuitous operator, then the superconformal descendant will also be a fortuitous. But is it only true in the n-fold premise, or?
That is generally true, because the argument is that these superconformal descendants are descendants with respect to the supercharges that commute with the particular supercharge that we are preserving.
In AGS3, The black holes in AG3 are described by some operator or heavy operator, but the descendant operator corresponds to the boundary gravity excitation of AG3, which is not a black hole. So
I'm not aware of the particular context that you're talking about, but I think it's possible that in that context, a different supercharge is used. So in here, it's just a simple algebra statement that we are looking for an operator that is annihilated by this particular Q, and then there are supercharges that commute. There are the subgroup of the superconformal algebra that commute with this supercharge. So if you consider descendants in this commuting subalgebra, not the full superconformal algebra, then the annihilation property according to this supercharge within a multiplet of the commuting subalgebra will be all homogeneous in the multiplet. So there are three mechanisms where non-core fortuitous operators can follow from core operators. And I hope you remember these 3 bullet points because they will come up again. 1, descendant. 2, graviton dressing. 3, brane or dual giant graviton dressing. So with these 3 points in mind, let me present the actual result, starting with the simplest non-trivial gauge group, SU2. So in SU2, by counting before constructing, we compute the non-graviton index. And this organization, the form of the non-graviton index, exactly hints at the last point that I mentioned. So there will be some core primary black fortuitous operators, and from that, the others will follow. There will be descendants of these core primary operators that show up in the index as this simple multiplicative vector. And there's also this geometric series vector that corresponds to dressing by any number of this particular graviton operator. So after factoring out this bullet point 1 and bullet point 2, the ways the non-core fortuitous operators can arise, the index crystallizes into a single infinite tower of core primary black hole operators that are all fermionic because of the minus sign, and that are all singlet in the global R symmetry.
Descendant number 1 is T dependent or just constant?
Yeah, yes, this is absolutely T dependent. Descendants will have more charges. So after we have
Question.
yes, please.
So in the finite n, how to distinguish between the non-graviton and also some graviton?
So we are looking at finite n, in this case n is 2 because we are looking at SU2 gauge group. We can write down an SU2 operator and we can imagine that we have the same multitrace operator, but we have larger n. Does it stay BPS? And if it does not stay BPS, it is a fortuitous operator. And if it does, it is a monotone operator.
Is it kind of physical argument based? I mean, because of graviton can be always part of the supermultiplet. So I guess I'm afraid I do not fully follow the argument fortuitous and the other such criteria
Since the
to
gauge group,
distinguish between the graviton and the black hole like.
since the gauge group and the superconformal algebra are totally commuting with each other, they are independent algebras. The descendant structure has nothing to do with the gauge, the increasing the gauge group. So we imagine increasing the gauge group to see if it's fortuitous or monotone, and that's not related to the descendant, the multiplet structure, if I understood your question correctly.
Okay. So please go ahead. Okay.
Okay, so we counted the fortuitous operator. It has crystallizes into a single infinite tower, and now we have counted. It's time to write them down. And this is how this single infinite tower of fortuitous operators look like. there's this first operator, and the rest of them can be written in somewhat recursive way.
What do you mean by single?
Because it's a single geometric series, there's one operator at order t to the 24, there's one at 36, one at 48, and so on. It's a single tower in that sense.
So that O0 is the operator with charge 24?
Yes, this is one with 24, and you can write down for any n, which will be 24 plus 12n order. And then we move on to the SU3 gauge group. So this table is the result of the counting the non-graviton index, and also after factoring out 1, the superconformal descendant, and 2, the geometric series vector, as we did for the SU2 gauge group. So after factoring this out, this is the complete list of, for now, the core fortuitous operators. We have organized into a table where vertical axis refers to the charge, the overall amount of charge J, and we have written down in thinking levels of the SU3 global symmetry group, which is the commuting part of the R symmetry group. Similar to the SU2 theory, there is this single infinite tower of the fermionic core fortuitous operators, similar to the SU2 gauge theory. But if you look carefully, there is an irregularity here. There is 24, there's one at 30, there's one every 6 order, but there's nothing at 54. So ever since we published this table in 2023, I could not sleep well because we must have done something wrong here in the last order that we could compute. But fortunately, very recently in December last year, these people, they decided to focus on the singlets, the 0,0 fortuitous operators only, and they could then project onto these singlets, such as you would do for the gauge group, calling it double gauging. And they obtained the spectrum of the singlet fortuitous operators to all orders. And that result confirmed this absence of the order 54. So I can now sleep well. Then this blue operators, the one on this second column, which are all fermionic, and also the first bosonic column of the tower of operators, that's where the brain-fused black hole operators, the black point 3, comes in. What are they? Suppose you have a fortuitous operator with SU3 gauge group, well, any one of these blue guys. Then imagine decomposing all the SU3 adjoint fields, the 3x3 matrices, in this block diagonal form, 2 plus 1 block diagonal form. If you decompose like that, this SU3 black hole operator will be schematically written as a product between a U1 part and an SU2 part. Now, if this U1 part turns out to be this single symmetrized scalar operator, and this SU2 part turns out to be a fortuitous black hole operator on its own, then we call this operator the brain-fused black hole operator in SU3 theory. That's because this symmetrized scalar operator has an ADS-CFT interpretation as dual giant graviton, and it is wrapping the SU2 black hole. I will talk about this interpretation a bit more in the next part. But this is how the brain-fused black hole, the black point 3, comes out from the core black hole operator. Then there are entries colored in cyan. These are operators that can be possibly, but we cannot prove. But with some convincing evidences, these are operators that are dressed by a combination of the gravitons and brains. So after factoring out all this non-core black hole operator, black point 1, 2, and 3, there are not many operators that remain as the core black hole operator. And can we write them down? Yes, for the first one. First one is this one at order 24. I should mention that this is not a black hole operator, but actually a black hole cohomology. I warned you that I will abuse the terminology. That means we have the freedom to add any Q exact term to this operator, and it will still be in the same cohomology class. hopefully it will be possible to add some Q-exact term wisely to turn it into a simpler, more elegant form, but that is a very hard computation. Then we have a little result for the SU4 gauge group. So similarly, factoring out the bullet point 1 and bullet point 2, the descendants, and the graviton dressing, we find that there should be 1 and 2 sets of graviton, non-fortuitous operators at order 28 and 30. And it's not very aesthetic that the simplest fortuitous operator in this theory is not a singlet in global symmetry group. So for that aesthetic reason, we suspect that these operators will actually be the brain-fused version of the SU3 fortuitous black hole operator, and that is the work in progress. But as you can notice from the emptiness of this slide, we have reached the limit of computational power. So that's why we are turning to other theories.
Some elementary question.
Yes.
So in the operator construction, why do you consider only adjoint scalar field? Because in n equal 4 supermultiplet, there are other fields, right? Like a gauge field and
You mean in the graviton operator construction?
Oh, I see. The phi, so graviton is only in terms of phi.
Yes. The gravitons all come from this single trace scalar operators and their descendants. So their superconformal descendants will include all fields that involve chiral linos and gauge field. It's included.
Is it more or less obvious?
Is it obvious? I think so in some way, because the ADS5 times S5 supergraviton spectrum derived by this Kiddy et al. 2005, they did it by Kaluza-Klein reduction, and this single trace with n scalar fields correspond to the nth spherical harmonic of in the Kaluza-Klein reduction in S5.
Okay, so but when you construct the BPS operator corresponding to the black hole light, then there are other operators are also showing up in addition to scalars, or?
In black hole like operators, absolutely. For example, the SU2 black hole operator, there are many numbers of psi and also F, the gauge field.
Oh, okay, I see. Okay, good. Okay, thank you.
And of course, there will be a superconformal descendants of these fields, which will involve more psi and F even.
Okay.
So let's turn to another theory, which in this time it will still be 4D n equal for Yang-Mills, but with different gauge groups, namely the SO7 and SP3 gauge groups. These two theories are S-dual to each other. So, for example, the SO7 theory with complex Yang-Mills coupling tau will be equivalent to SP3 theory with complex Yang-Mills coupling minus 1 over tau. But despite this S-duality, these two papers found that these two theories have different cohomology spectrum. In fact, they found that SO7 theory, compared to the SP3 theory, contain two additional supercharged cohomologies, one fortuitous and one graviton. So what's happening? What's wrong with the S-duality? The point is that when I say cohomology spectrum and supercharged cohomology, I was always referring to the classical, the tree-level cohomology. But the S-duality is a weak strong duality. SO7 theory at weak coupling will be dual to SP3 theory at strong coupling. So when we find the difference between the two theories, it's actually telling you that the cohomology spectrum is different between the weak and strongly coupled regime of the same theory. And it is known in general that in a gauge theory, as you change the coupling constant, an operator can lift to be a BPS operator can lift to non-BPS by gaining some anomalous dimension. But that can only happen in a pair when another operator also lifts to non-BPS at the same time. so they can form a long representation of the superalgebra together. Two of my proud collaborators, Choi Jae-hyuk and Yoonu, found that this is precisely what's happening to these two additional cohomologies. If you consider not just tree level, but quantum correction to the supercharge, then this Q acting on this one of these cohomology will become, does become the other cohomology. Meaning that although these two were independent cohomologies, supercharged cohomologies at the tree level, now because of this relation at quantum level, OF is no longer Q closed and OM is now Q exact. So these are, neither of these is a cohomology at the quantum level. So the puzzle against S-duality has been solved, but this is a solid counterexample where the non-renormalization assumption that everyone has been taking when they study the weakly coupled regime of the field theory is now in danger. They proved that the first SU2 black hole operator that I showed you is safe in this quantum correction, but all the other operators, SU2 and SU3 black hole operators, are in danger and and it is an open problem to find out what happens to them at the quantum level. And in this paper, they derived the full one-up correction to the supercharged Q. So now we have a tool to actually explicitly check what happens to all these operators at the quantum level. And I heard from a new student, Park Ji-woo in Seoul National University, that he also found some examples of this kind of quantum lifting even in the unitary gauge group, in the simplest SU2 gauge group.
Wait, is that lifting and resolution of this mismatch happens by considering model effect?
Yes.
Then, so non-renormalization assumption is in danger of classical level, right? So at one loop level, if you consider all one loop effect, maybe the issue goes away. Possible, is still possible.
So what I call tree level is the first level of supercharge, which already includes some Ji-Yang mills. So it's different from the free theory that we often say. So in some sense, that's already one loop, and this is two loop. But yes, but this is the tree level supercharge. So in that sense, we are calling this one loop. All right, so this was the lesson that we can learn from the other gauge groups, that non-renormalization assumption is broken. And let me briefly mention some other theories. Fortuitous operators have been found in ABJM theory, and also its generalization, where the two nodes of the gauge group, UN and UM, are different. One interesting phenomenon here is that because of this UN times UM, there are two separate layers of fortuity. In a UN times UM gauge theory, to construct a gauge invariant operator, you can multiply a bifundamental times anti-bifundamental to define an n by n matrix and take the trace. Or you can multiply the other way to define an m by m matrix and take the trace. Then an operator can be fortuitous with respect to UN trace relations, but also with respect to UM trace relations. That means when n and m are taken to be very different, there are two clearly separated layers of fortuity. And as you bring n and m close to each other, that will interpolate to the ADS4 black hole states that are being dual to the ABJM theory. Then there are simpler models, such as the famous n equal to supersymmetric S5K model. And there's also a fermionic matrix quantum mechanics model that is specifically designed to study this fortuity phenomenon. One notable feature of these theories is so-called the R charge concentration. So if you consider fortuitous operators in these theories, if you consider the distribution of the fortuitous operators in the charge space along the charge space with respect to the global charges, the fortuitous operators are concentrated at some point or along some curve, something with a codimension, as if they satisfy some constraint. And this is a curious feature with relation to a famous constraint on the supersymmetric ADS black hole charges. All ADS supersymmetric black hole are known to satisfy a charge a nonlinear relation between the charges. between the charges of the black hole solutions. Another interesting feature of these two models is that they are not dual to any black holes. And people sometimes talk about the SYK model being dual to some ADS2 gravity, but to say the least, the typical holographic statement that there is a black hole and there are QFT operators dual to the black hole, it doesn't hold naively in these two theories. So this is an example where we can define the idea of fortuity without a dual black hole hanging around. Then the honorable mention goes to the two other theories in the list, and then I will turn to the last part of my talk. So in this part, I will talk about what this fortuity program, this classification between gravitons and black holes actually tell us about the black holes themselves. So recall these two ways in which the non-core fortuitous operators could follow from the core fortuitous operators. There was this graviton dressing where you multiply a black hole operator by some graviton operator to produce a new black hole operator. And there's this brain-fused black hole where this U1 times SU2 decomposition revealed the structure of this dual giant graviton times an SU2 black hole being a new SU3 black holes. On the other hand, there has been a recent series of work in a very different point of view on ADS black holes. It is about the stability of ADS black holes. The bottom line of that research is the following. When an ADS black
element together, how do you distinguish these two operators? I still don't understand.
These two graviton operators, it is possible that these two things happen in combination. There are actually examples of that. But simply, if you have a certain operator, maybe the simplest fortuitous operator in each gauge theory, you can believe that that is a core operator because it's the simplest in the gauge group. But then you can multiply this kind of simple graviton operator.
F is a fortuitous or
Although F is the gauge field.
gauge field.
F is the gauge field.
That's the difference between graviton and brain.
So this, of course, you can. I think you're asking because this can also be looked as a graviton.
Yeah.
Yes. So this is not a simple product actually, and this is a U1. I wrote it as a trace, but this is a U1 operator, so it's actually not even a trace, but just a simple product between a U1 component of the scalars. And this is an SU2 black hole operator, and this is an SU3 black hole operator. So the similar sign, this contains a lot of skipping. Actually, it's not a simple product. That's why we call it brain-fused black hole operators. I can explain more in detail later.
So you're saying, so I know that, for example, in large N, there's a scaling difference. Like for graviton, it's order 1 charge.
Yes.
Brain, it's order N. It's typical distinguishing argument. But here, because you're discussing this in like N equal 2 and 3, that distinguish is
Yes,
not work.
yes.
So there must be some structural difference between graviton state and brain state, right?
Well, if you look at this operator, actually, they are structurally very different. Yes. So this SU3 black hole operator, this kind of structure will only reveal if you do a 2+1 decomposition. If you turn on the off diagonal components, this kind of structure will never be visible. But here it's a simple product between two operators in the same theory with the same gauge group. So to continue, the over-rotating ADS black hole, when it has large angular velocity, it will spontaneously emit graviton that carry large angular momentum, because that way the entropy is increased. It's called supervariant instability. And the result of the instability will be a two-component system called gray galaxy. It's a black hole surrounded by a graviton here that already rings a bell. And then if an ADS black hole is overcharged when its electric potential is larger than 1, then it will spontaneously emit dual giant gravitons. which will carry large Q, the R charge. And as a result, it will become a two-component system called dual-dressed black hole. As you can notice, there is a conceptual analogy between how the operators are dressed in the field theory and how the black holes are dressed in the gravity theory. For the graviton dressing case, this operator, the graviton operator that's dressing the black hole operator, is only allowed when it has large angular momentum. And that fits this picture in gravity, where this gray galaxy is a black hole surrounded by a graviton hair with large angular momentum. For example, it is known that the graviton in S wave, the lowest partial wave, is not allowed to dress an ADS black hole to form a hairy ADS black hole. The brain-fused black hole picture, as I already explained, this operator has an interpretation in ADS-CFT as dual giant gravitons, which are D3 brains wrapping inside the ADS5. And it is also known that these D brains, they reduce the flux N by 1 inside compared to the outside. And this operator fits that picture precisely because it's an D3 brain wrapping an SU2 black hole that overall look like an SU3 black hole when seen from the outside. So let me finally conclude with some open questions. I will present 3 open questions that have actually appeared throughout the talk sooner or later. The first one is about the quantum correction to the supercharge. As you saw, there has been a counterexample, in particular with these gauge groups in 4D equal for superharmonious theory, where BPS operators lift at quantum level to become non-BPS, breaking the non-renormalization theorem, or there's not a theorem because it's broken, maybe non-renormalization assumption. Then it remains to answer, is there a non-renormalization theorem? And if there is, to what extent is there a non-renormalization theorem? And if there's not, how is the quantum correction to the supercharge going to change the picture? Is it going to change the picture drastically? That's one open question that also involves some work in progress.
Is there any known result for SU and NN?
Yes, it is not, it's being recorded, so I have to be careful. But for SU2 theory, I heard that there was a preliminary result in Seoul National University that they found some such examples of quantum lifting in the SU2 gauge theory.
So there will be a correction.
Yes, for the one-loop quantum correction. The second open question is about the R charge concentration and the supersymmetric ADS black hole charge constraint that every supersymmetric ADS black hole are known to satisfy. As I mentioned, it is observed in simpler models such as the S5K or fermionic matrix quantum mechanics model. So one can ask the following question. In a more complex theory, like 4D n equal for Polynomials, that has the black hole dual, and that black hole dual satisfies the charge constraint, now let's consider the fortuitous operators in 4D n equal for Polynomials theory, and consider the distribution of these operators along the charge space according to the global charges. Are these operators really concentrated on that codimension 1 surface, the same surface as the charge constraint surface? The answer is no, but it's all right, because it's not that all black hole has to satisfy this charge constraint. It's only the core black hole that has to satisfy the charge constraint. For example, the gray galaxies and dual-dressed black holes, they do not need to satisfy this charge constraint. So we can refine the question like this. Can we make a complete classification between core and non-core black hole operators, and now only consider the core black hole operators? Will they be concentrated on this charge constraint surface? The last question is a bit more vague, but perhaps more far-reaching. As we have noticed, this idea of fortuity is perfectly well defined in theories that does not have a dual black hole, although this concept was motivated by trying to classify gravitons versus black holes. So what is the true meaning of fortuity? At this point, it seems like the fortuity is a property in quantum theories that come in series of n, where you can consider a series of theories labeled by n, that show some properties such as being chaotic, ordered, things like that, that happens to coincide with the notion of black holes when it comes to the holographic theories. So that being said, can fortuity broaden our microscopic understanding of black holes? Thank you for your attention.
Okay, thanks for the interesting talks. So now we're gonna have Q&A session. So please ask him about your question, including on June.
I just have one question. So, please let me know if I'm wrong. So you said even if n goes too large, if j scales like n squared in the limit,
Yes.
of course it's gonna be possible to explicitly construct a formula because j is gonna be less. But still, in that sector, large charge sector, in principle now, since fortuitous states can exist.
Yes. Yes. And it must. Yes.
Yeah, then my question is, previously I thought gravity dual of such like dressed state. Dressed state itself is formal fortuitous state, right? So it's dressed by graviton or grain.
Fortuitous states dressed by,
Yeah,
yes.
that's also fortuitous.
Not always, but
Not always, but
certain dressings.
Yeah, some
Yeah.
cases.
Yes.
But now these are like assumed to be dual to this gray galaxy or something
Yes.
like that.
Yes.
I thought because this is fortuitous state, the dual gravitational solution cannot be constructed in the semi-classical limit because semi-classical limit is n goes to infinite, and I thought this kind of state does not appear in n goes to limit. But now, can I say if J charge scales like n squared, you can still imagine the possibility of constructing semi-classical dual solution without any problem?
I think this is a very confusing thing to say because our understanding of infinity is very limited. I mean, even if you take n equal to, even if you take large n, when you're talking about all these things, you have it finite.
Yeah.
You must have it finite. You need to be able to think some number that is larger than n. So in that sense, n has to be finite. And then, of course, yes,
But
absolutely.
still, in principle, there is a possibility of having some semi-classical well-defined dual gray galaxy solution. Because as far as I know, the gray galaxy is not just written as an exact solution to the
Right,
programming
right.
equation. But is it, in principle, there's a chance for such a solution to exist? Or in principle, it's impossible? I have questions.
That is something I'm not very qualified to answer, I think, because that's the research in the bulk direction.
Yeah.
But I think yes. For example, I'm not sure if it's completely relevant, but there's this small ADS hairy black hole solution actually with perturbative graviton hairs by considering some consistent truncation where you have a single scalar in addition to the supergravity fields. And like Minwala, Papadodimas, they in 2010 they found the perturbative solution to the ADS black hole. They call that hairy ADS black hole.
So any other questions?
Yeah, I have some, I guess, out of curiosity, maybe it's different from the main line. So you considered SO7 and the SP3, right?
Yes.
So if we consider large n, SUN and the SO2n plus 1 series, or even SO2n, in a very large n, usually SUN can be embedded group theoretically.
Yes.
And maybe that may mean that the states classification, there may be some relation between the SUN and the SO2n plus 1 or SO2n. And that kind of some qualitative properties are occurring in your SO7 analysis by comparing with the SU3 results, or and what is it? I mean, if there is some relation.
So SO7 or higher SO2n plus 1 gauge groups, they do embed in some sense the SU smaller n gauge group.
Right.
Yes. And maybe it is possible to consider something similar to what we did for the SU3 being decomposed into 2 plus 1 block diagonal form. Maybe you can consider a similar restriction of the SO, for example, SO7 matrices.
So can you rephrase that in terms of the black hole-like states and or graviton-like states between those two different series?
So first of all, even if you can embed certain SU n gauge group into SO7, the spectrum will certainly be different between the two theories. It's a two different theories.
Right,
But
right.
yes, maybe you can deduce some interesting properties, such as the brain-fused black hole we did for SU3 from that relation. We have never tried that, but I think that's one thing you can try. Yes.
I see. Okay. Okay, thank you.
So anything else?
Okay. So when you say black hole, you mean really literally some object with the horizon, or can it be naked single object?
So that's also one open question that I did not list in the 3 open questions. So we, in holographic sense, we actually simply classified gravitons versus something that is not graviton, just assuming that will be typically black holes. And now you can ask, what does the individual black hole microstate correspond to in the geometric side? There are people working on that question, especially people who are working on the D1, D5 system. But I don't think I have the answer to that question. Yes, does the individual microstate correspond to horizonless geometry, or
But in principle, holographic dual should include naked single object. Or not?
I don't know.
So maybe 수공을 해볼 때 어둠이 naked singular also. I wonder whether they are captured by dual CFT.
Are those states going to be included in the index?
That's captured from CFT side.
I don't know the answer.
So, the simple question. So, suppose we have a any content limit and we have superiority in 85, maybe we have a black hole. So, do you think there exists, in the super young side, there exists a process of which is overall dual to such a black hole? Because I think it is safe to say in large N limit, the black hole is dual to some very complicated ensemble of the
Yes.
states. So yeah, so if we have such a dual state of like a great galaxy, then in the larger limit, that great galaxy should not be an individual solution of the supergravity, but they might be inside of the ensemble of the usual well-known ADS ADS black hole. So my question is that, do we have great galaxy as a semi-classical solution of the supergravity in ADS5? So I would ask your opinion.
The viewpoint I have is that in supergravity theory, there will be a solution, a black hole solution, and then so you're asking. So in gravity theory, you can consider gravitational path integral, and where the black hole solution, the core black hole solution, arises as one of the saddles. And then in the gravitational path integral, the partition function, the dressed, like something like dual dressed black hole, will appear not as a saddle, but something. So is that what you're suggesting? So those kind of solution, the non-core, the dressed black hole solution, will not appear as a new independent saddle of the partition function, but as a some kind of something multiplying the partition function as if there are two separate parts of the system.
Right. That's what this, ask your opinion, but anyways, so let's suppose that we don't know the answer. And I also have one additional comment about Professor Jung's question. So black holes are silicon. How about the naked singularity? Are they silicon?
I don't know about naked singularity, so sorry.
I mean, no one knows what actually needs to be included in the gravitation path interval. I mean, there are some proposals, but there's no golden rule.
So the black holes are singular at r equal to 0, but actually it is hidden by the horizon, so it's safe to perform the path integral.
But no one has proven that it has to be included, right? That's what I'm saying. So